Good morning, and thank you for joining us. Today's webinar is on detection limits. How low can you really go? Joy Osborne, our TOC product line manager, is presenting today, and we will be taking questions, so feel free to submit the questions throughout the presentation, and I'm going to hand it over to Joy.
Thank you for that introduction, Shelley. Hello, everyone. I want to start off by thanking everyone for joining this live webinar on detection limits. How low can you really go? The reason I chose this topic was I get this question often in regards to our instrumentation. Everyone wants to know what the detection limit is for each of the instruments we manufacture. I struggle to respond to this question every time. It depends on which type of detection limit you're referring to, and most of them are actually theoretical. There are so many kinds and definitions, therefore it is such a loaded and complicated question to answer. I can't just give a short response for it. Therefore, I'm going to take 30 minutes today and help explain it so everyone can understand it better and why it can't be so quickly and simply answered. So you know, Teledyne Tekmar manufactures volatile organic compounds, total organic carbon, and semi-volatile organic compound chemical instrumentation. All instrumentation is proudly made in America from concept to design to finished product. With all our instrumentation, we give an analytical range and detection limit. There's a lot of testing that goes into establishing this low range. We use a theoretical and statistical value, which is in accordance to EPA guidelines, but this does not mean that it is always quantifiably achievable in real-world testing. I can understand this can be quite frustrating to the average analyst, which reads a brochure that has an analytical specification and then buys it and thinks they can achieve those exact numbers. This is why we need to have this discussion. All right, so today's agenda will be defining detection limits, which is not a simple task, so we'll go over that. Explaining detection limits of method detection limit, limit of detection, and limit of quantification through the new Lodix TN. And then we'll be comparing an NDL to LOD and LOQ. And then finally, I'll be giving you several detection limits for our new Lodix TN. So you're probably wondering, what is the Lodix TN? The Lodix TOC combustion analyzer is designed to accurately measure carbon content in aqueous matrices down to the parts per billion level. This is where we're referring to detection limits when we say parts per billion level. It uses proven high temperature combustion, oxidation of carbon material into carbon dioxide, and detection using a new non-dispersive infrared detector. The Lodix is the ultimate solution for wastewater, surface water, groundwater, seawater, and any other hard to oxidize matrices, and has an economical price to fit any lab budget. Also pictured to the right is the Lodix solid sampler, also known as the LSS boat. The LSS quickly prepares samples for TOC and TC analysis in a wide range of sample matrices that include wastewater, sludges, slurries, and solids. And pictured to the left is what we'll be talking about today. It's the new Lodix total nitrogen module. It analyzes samples for total nitrogen content. The TN module works in combination with the Lodix TN analyzer, enabling analysis of aqueous samples for TOC, TN, TC-TN, and TN analysis. The results from the total nitrogen module will be used to demonstrate different detection limits throughout this webinar. All right. So here are some different types of detection limits. Limit of detection, limit of quantitation, method detection limit, critical level, practical quantitation limit, minimum level, instrument detection limit, lower limit of detection, estimated quantitation limit, reporting limit, minimum reporting limit, estimated detection limit, minimum detection limit, quantification level, sample quantification level, and minimum analytical level. And there's actually many, many more. I just couldn't fit very many more on this slide. So you're probably thinking, oh my goodness, there's so many. Well, I possibly can't cover all these in 30 minutes, but I'm going to stick to 3 important ones: the environmental industry, which is a limit of detection, limit of quantitation, and method detection limit. And I also want to note that there's, sometimes the same abbreviation actually stands for 2 different types. So MDL here means method detection limit, but it could also stand for minimum detection limit. So make sure you clarify that. Okay. All right, so if you're not already confused enough, I know I was when I started looking into this, it's actually by state. So here's an example of a couple different states with summary of analytical detection and quantification terms. So before you get started establishing detection limits, you definitely want to check out what your state requirements are. All right, and here are the LODIX TN analytical specifications. These are the specifications we give on brochures, any kind of marketing information. So the LODIX has a concentration range of 0 to 20,000 parts per million without dilution using a single 0.5 mil sample injection. Has a limit of detection of 50 parts per billion, which we'll discuss what that really means in this presentation. It has carryover of less than 1%. And it has 2 different sample sizes of 0.5 mils and 0.3 mils, which is used for salt samples. So you actually want to use less sample because it's hard on your catalyst when you have salt samples. The precision is less than 2% RSD for a mid-range standard. And of course, analytical performance is affected by your reagents, water, gas, and all those kind of things. So now let's look at the new total nitrogen module. Its range is 50 parts per billion to 100 parts per million. Its precision is less than 3% for a mid-range standard and triplicate. Its carryover is less than 1%. Its sample size is the same. You can use 0.5 or 0.3 if it contains salts. So you're probably wondering, what is the detection limit for the total nitrogen module? Well, let's go through the motions, okay? So like I said earlier, I'm only focused on 3 definitions because I only have 30 minutes. I would love to cover them all, but that would take all day. So we're going to focus on method detection limit, and it's defined as the minimum concentration of a substance that can be identified, measured, and reported with 99% confidence that the analyte's concentration is greater than 0 and determined from analysis of a sample in a given matrix containing analyte. And this is the definition given by the EPA. Like I said, I was going to concentrate on environmental definitions. And then we have the limit of detection. The lowest concentration level that can be determined to be statistically different from a blank. And finally, the limit of quantification, the level above which quantitative results may be attained with a specific degree of confidence. All right, now don't give up on me now. I know you're probably rolling your eyes and you're still like, I have no idea what this means. And that's okay. We'll explain each one of them much more thoroughly here. All right, so before you start to determine, any kind of detection limits, here are some tips and tricks to get started. You always want to make sure your glassware is clean, and whatever analyte you're looking at, in this specific case, it's nitrogen. So you want to make sure you use, don't use any cleaners or soaps that contain nitrogen or will contaminate it in any way. So don't use like nitric acid or something like that. Otherwise, you're not going to get good MDLs. You got to look at the purity of your reagents and your water, the highest possible you can find. And I did this for the study. I pretty much replaced all the consumables on the instrument before I even got started, just to be safe. All right. And then you should clean out your system. So I ran several rinses before I even got started and make sure the whole system was clean and flushed out before I started looking at detection limits. All right, now you're probably thinking, well, which concentration should I start at? And this is a difficult question, and it may take some playing around with. So when I got started, I ran a 10 ppb, a 20 ppb, a 50 ppb, and 100 ppb. And then I looked at the signal to noise ratio. So here is the baseline, the noise. You can see, it's really hard to see in this presentation, but the height of the absorbance is about 0.1. And then this is a 20 ppb standard, and you can see the height of it is about 0.5. So you want to start with a concentration that is 2.5 to 5 times the signal to noise, or you can use 3 times the standard deviation of reagent water. So you can run some water and figure out where that's at and compare your standards to that. Or you can start where there's a break in the low end of your calibration curve. So I did this testing, and I determined from this that I wanted to start with 20 parts per billion. And here's the math, just in case you couldn't figure that out. All right, so let's go on to method detection limits, which was the first definition that I provided. All right, it's a way to qualitatively, not quantitatively, see a target analyte. So please keep that in mind. It's really just a means of measuring reproducibility. It just demonstrates the ability of an instrument to prepare an identical low concentration. And by that, it means, you as the analyst and your reagents and all that kind of things go into play about how well you can prepare that low end standard reproducible. And it's basically an MDL is where the level should be 50% detectable, 50% not detectable. So this number, when you get this number, 50% of the time you're not going to see it when you actually run it. So please keep that in mind. And it's also defined that you have to analyze at least 7 replicates of your concentration, which I did. You can do more, but it is specified that you need to run at least 7 replicates. And then you find the standard deviation of the 7 replicates or more. And then you look up the student's t-value, and you will multiply that. So let's go over how I went about doing this. So here's a calibration curve. This is a normal calibration curve on the Lodex TN, just to demonstrate the range. I'm not talking detection limit here. I'm just talking the range of the TN detector. I was able to run it from 0 to 100 parts per million and still receive a good R-square value. I like to get at least 3 9s. That can be up to your SOP. So I was able to do this. But I would not recommend using this calibration curve for a detection limit study. I would hone in on the low end of that calibration curve range. So I rewritten the curve, and just so you know, this is what a report out of our Lodex TechLink software looks like. So I rewritten a curve for the study. I ran a 0, a 20, a 200, and a 500 parts per billion in triplicate. I did force that curve to 0, but just so you know, it's not always achievable depending on the instrument, but I was able to do it and still get, again, good linearity. I got at least 3 9s, which I like to see. And it's important that when you're looking, I already established that I wanted to do 20 ppb, that you have a point below and a point, at least 1 point above in your calibration range to do this study. So I wanted to make sure I had points on either side of that MDL. Okay, and then I started running it. Like I said before, you need to run it at least in 7 replicates, which I did. And here's the results. So for the first rep, I got 23 parts per billion for a 20. And you know, it varies. There is some variance from run to run, but remember this is the low end of the detection limit. And even though there is some variance, it still looks pretty good to me. There was still an RSD of 11 or almost 12% here, and the average still worked out to be 20 ppb, which was really, really nice. And from our software, it actually calculated the standard deviation for us, which is 0.002 parts per million, or 2 ppb. All right, so now that we have our standard deviation, we can go to calculate it. So this is the formula for MDL. So the formula is the t-value times the standard deviation. So the t-value for 7 replicates is 3.14. If you did more, you know, you can look at that t-value chart. I just listed a couple here. So if you did 8 reps, it would be 2.998. If 9 reps, 2.896, and so on. And then times the standard deviation, which was given in the previous slide as 2 ppb. So when you calculate that out, your final result for MDL is 6.286 parts per billion. There are some guidelines that you want to keep in mind. The first guideline being that the calculated MDL must be less than the spike concentration, but greater than 1/10 the spike concentration. Okay, so the spike concentration was 20 ppb, so 1/10 of that would be 2 ppb. And 6.286 definitely falls between 10% and 100% of that. So that's all they're saying, is this MDL number should be more than 1/10, but less than what you were actually running. If it's not, then you need to find a different level to run it. All right. All right. So, and then the second rule is it must be distinguishable from a reagent blank. That's pretty easy to do with nitrogen. You pretty much, when I run like a DI water or blank with total nitrogen, you should get pretty much nothing. I might get a couple of ABS just because it will pick up some noise from that baseline, but there really isn't any that should be in your blank. That's not true for TOC. There is some carbon even in DI water, so that would be a little bit different, but you can also just figure that out from your signal to noise ratio. And then the third guideline is the spike level, which is 20 ppb, should be less than 5 times the MDL. So if you calculate that out, it should come out correct. And then, so what does this really mean? So the point of this was there's a 99% chance that 6.286 parts per billion is above a blank. So that's all it's saying, is if you run 6.286 parts per billion sample, you have a 99% chance that it will come out above a blank. That's all it's saying, okay? Okay, so what are the limitations after I kind of went through the math and everything with you guys? Well, MDL is at a 99 confidence level, which is stated in the definition, but this still gives you a 1% chance there's false positives. So you could get a blank that gives you a false positive, and then it assumes a normal distribution curve. So if you remember those curves back from statistics and probability, it would be a symmetrical curve, which may not in fact be the case at all. And another limitation is you base this number on a solitary, just one instrument. You know, I was the only analyst and one calibration. And you're allowed to do this, but, you know, over time it could change. Your MDL could change. Your instrument could change. All those kinds of things could change. So it's just a one moment in time kind of number. All right, so now that we've explained method detection limit, let's go over our next detection limit term, limit of detection. So the limit of detection is the lowest concentration level that can be determined to be statistically different from a blank, and that's given from American Chemical Society. The limit of detection is equal to 3 times sigma. You can run it as a 0 or blank, or the lowest level of measurement. So it's up to you if you just want to use like DI water or what you want to use for this one. It seems a little more relaxed. And sigma is the population standard deviation. It implies an infinite number of analysis, but of course it's not. And there is no minimum number of replicates needed. Like with MDL, it said there needs to be at least 7. There's no guideline for that. So just to show you how it's different, I just did 4 reps of water, okay? And I still got the same standard deviation, which is 0.002. Somehow, I think I just lucked out on that. I'm not sure. Or it really is a measurement of the instrument, how much it can see between each rep of a sample or blank, basically. So I got the same standard deviation. All right, so let's calculate it out. It's really easy. It's just 3 times the standard deviation, so you get 6 parts per billion, which I know it's not that different from the last calculation of MDL, which was 6.286. You got a very similar number, even though you went about it slightly differently. All right, now let's talk about limit of quantification. Okay, this is a little more strict. It's a higher number usually. It's 3.33 times the limit of detection. So I could take that last number and times it by 3.33. But for this study, I went through the whole thing again just to kind of show you. And just as a reminder, the definition of limit of quantification is the level above which quantitation results may be attained with a specific degree of confidence. All right, so let's calculate it out. The formula for it is 10 times the standard deviation. I used the previous report I showed you guys earlier. You know, the standard deviation was 0.002, so 10 times 0.002, again, very easy math, which is your final result is 20 parts per billion. Okay, so the limit of quantification is definitely much higher than the limit of detection or the method detection limit. So let's compare them a little bit. So these are the results I got for each test. Now keep in mind it's the same instrument, it's pretty much the same data, it's the same calibration curve I used, but I still got 3 different results. So in the MDL is the minimum concentration measured with 99% confidence that it's above a blank. The LOD is the lowest concentration difference from a blank. And the limit of quantitation is the level above which quantitative results have specified a degree of confidence. And it's true, the LOD should be roughly equal to the MDL, which is what I got. So I was pretty happy with that. So in conclusion, each with its own definitions and calculations, but sometimes they are actually related. So if you look it up, the LOQ should be 3.33 times the limit of detection and 3.18 times the limit of quantification, which if you go back and apply it to the math, it's correct. So I was happy when that happened. It all worked out. True quantifiable detection limits will vary from instrument to instrument because it's analysis dependent, calibration curve dependent, instrument dependent, it's reagents, water and gas dependent. All that goes into those calculations. So, you know, I could run it in my lab and get 20 parts per billion for the limit of quantification. You could even take that same exact instrument and run it in your lab and get different results. So that's really why it's so hard to tell people like what the detection limit truly is. It just varies greatly from instance to instance. So the whole point of the study was establishing the detection limit of the LODXTN module. So for this particular LODXTN module, at the time it was run, you could either say it's 6 parts per billion, 6.286 parts per billion, or 20 parts per billion. or possibly something else, depending on what kind of detection limit is utilized. So just keep that in mind when instrumentation companies print that in their brochure, and take it with a little bit of a grain of salt that there is some kind of wiggle room sometimes in that. And that's me being honest from working at a chemical instrumentation company. Okay, so I see we're at the end of our 30 minutes, so I just want to thank everyone for taking the time out of their busy schedules to listen to this webinar. I hope you feel a little bit better about what detection limits mean, that you learned a little bit. If you want more information, we do have Facebook, Twitter, LinkedIn, and we even have a blog that talks about current topics, which is sometimes really interesting. And then we constantly have new webinars coming out, application notes, and new products. So stay tuned for that. And if you have any questions that you think of after this, you can type it in the box right now if you can think of it now. But if you think of it later, like, oh, I really wish I'd asked this question, please feel free to email me. My email is just my name, joy.osborne@teledyne.com. So feel free to do that. And then if you want more information on the new LoadXPN module, please visit our website. All right, so give me a second to pull up any questions.